The New Future of Making on Mars, a tutorial conference for students. Discover possibilities for you to take part in the exploration of Mars. 5 tutorials, 1 plan for building a science station on Mars, 1 veteran's guess about the future, 1 super interview on hot robotics in Leo, 1 conference summary, 8 subject matter world experts from NASA, top universities, and 3 space companies. Sponsored by the Mars Society of Canada, Maker Works of Ann Arbor. Organized by 2 Planet Steel. See possibilities you haven't seen before. Now one of our 5 tutorial videos from our conference for students. In this one, Joseph Palmowski gives a talk titled RedWater, Mining for Water on Mars. In it, Mr. Palmowski explains how to extract water from subsurface glaciers on Mars using coiled tubing and the Rodwell method. Joseph Palmowski is a RedWater project lead and a systems engineer at Honeybee Robotics, a Blue Origin company. NASA has funded the RedWater project since 2019. It is NASA's principal funded project for extracting water from Martian subsurface ice. Honeybee Robotics is the project's lead organization. Other organizations involved include the Planetary Science Institute, MIT's Haystack Observatory, and Michigan Technical University. Learn and enjoy as you hear Joseph Palmowski's expertise on mining Martian subsurface water ice. This talk will benefit you, since extracting water is certainly critical for the next 10 and more years of Mars exploration. The meanings of some technical terms are given below in the video's description.
So, hi everyone. I am Joey Palmowski. I'm a systems engineer at Honeybee Robotics. I've been at Honeybee for about 8 years now. So I'm going to be talking to you about RedWater. It's a subsurface water mining system designed to extract water from usable resources on Mars. So let me quickly talk about Honeybee and who we are. So we were founded in 1983, so definitely not a new company. We were purchased by Blue Origin in 2022. Sit around 400 employees across our 2 divisions, one in Longmont, Colorado, which is primarily what we call our motion control division. We're manufacturing at the subsystem component level, and then there's the exploration technologies, which I'm affiliated with, which is out of Altadena, California, which is only about a couple miles from JPL, if you know where that is. So at exploration technologies, we're vertically integrated, so we do everything under one roof as far as mechanical systems, avionics, software, and even mission ops as well. Right now we have over 50 flight programs across NASA and commercial space on here. So our exploration technologies group focuses on 3 major competencies. So robotic platforms, so that's going to be robotic arms, power systems, mobility and deployment systems, and then avionics and software, and then tying those things together. We also focus on mining in ISRU, so volatile extraction, excavation, sorting, and beneficiation. And then third is going to be subsurface exploration. So that's your robotic sampling and drilling systems, collecting samples at the surface and processing those, then geotechnical instruments and biological instruments as well, and then planetary protection and contamination control. And RedWater sort of sits right at the intersection of the ISRU and the subsurface exploration components here. So what is RedWater? At a high level, it's subsurface water mining technology to support ISRU on Mars. So the idea is that we want to drill through the regolith overburden into these ice-rich subsurface glaciers to access, what we think is fairly pure ice sheets, and then we can use heaters embedded in the drill or heating and circulation to the surface to create a melt cavity called a Rodwell. And then we can pump water to the surface to extract it, but we can also recirculate to continue the growth of that well until we're too deep or too large of a well to make it efficient enough to continue. As far as the technology goes, in a nutshell, we're combining 2 terrestrial concepts that are pretty well established. I'll talk about these a little more, but it's coiled tube drilling with a Rodwell, which is this concept of the subsurface water well, which is a fairly established, well understood concept already in the Arctic and Antarctic remote locations. So looking at ISRU as a mission, like full mission architecture, here on the left is the RedWater system itself, which is responsible for drilling down. Where right now we estimate potentially as shallow as 10 meters we could find ice. The system is designed to be actually potentially deeper than that as a sort of a being risk adverse. And then the system's capable of actually heating and melting, extracting the water to the surface. And that's sort of what RedWater is responsible for. And then, of course, for the full architecture, you're going to be doing something with that resource, right? So the water can be routed to either life support needs for a crewed mission, but most importantly, or at least the highest use case is going to be propellant production. So storing and transferring this water to a propellant production facility that uses both water and atmospheric CO2 using Sabatier to produce your O2 oxidizer and then your methane fuel. And then, a couple like baselined other technologies here, but these are not within the scope of RedWater, just looking at the high level architecture. Moxie was a demonstration of capturing atmospheric CO2 at a very small scale, but at least proving out that technology. So that was a good step in the right direction. As far as power generation, it's believed that'll most likely be a nuclear power source for the level of power that's needed. And there's been some development there and seems to be ramping up as well. As far as, what the vehicle will be, Starship seems to be sort of the baseline right now. Starship is also a very propellant needy architecture. So that's, we've baselined a volume of water needed for Starship, but some of the MAVs that have been proposed would actually potentially need much less water. So this is sort of a worst case scenario for getting off the surface of Mars. So as far as the system ConOps, I'll walk you through that real quick. So initially you do a drilling operation. So again, there's some uh, top overburden layer that we expect to be some combination of regolith, potentially rock or ice cemented regolith, and then start to transition to potentially permafrost, but at some point reach a more pure ice layer. And so as we're drilling, we rely on a rotary percussive drill at the tip. I'll talk a little more about that. And then we use compressed gas from the surface. We release it at the tip of the drill, which draws the cuttings out of the borehole to continue downward. The coiled tubing that we're using to deploy the drill can also provide weight on bit for the drilling process, but it's also a natural conduit for your gas lines to transport your pneumatics downhole, but also your electrical systems that need to be powered from the surface. Step two of the ConOps is once you reach that target ice depth, you perform borehole sealing with what we call a packer. So you do that in order to pressurize downhole. You can isolate from that low atmospheric pressure of Mars, which is right around the triple point, so you can maintain liquid water. And then once you have a nice primed well that you're able to circulate water back to the surface and heat in return, you can then inflate your packer, assuming it should already be inflated at this point, and then you can actually, instead of pumping, an alternative trade is you can actually do positive pressure to push water out. So there's sort of two open trades for this initial development. We looked at a positive pressure, but you could alternatively use a pumping system from the surface. You need to melt the well. And then that last step is the pressurization and water extraction. So looking at sort of the fundamental enabling technologies here, one of those is going to be this concept of coiled tube drilling. So this is not something that we invented. It's been around for a very long time in energy industry. It's typically a much better alternative than using these continuous added drill strings. So it's a much more intensive process to do that, larger surface footprint, so they can significantly reduce the infrastructure required. And that's particularly beneficial in, a remote location where you don't want to haul a lot of equipment in and out. Still like fairly large trucks and mobile systems that have to move these out. RedWater has the benefit of not needing to go nearly as deep as some of the terrestrial stuff that's going like potentially kilometers deep for their objectives. We're looking, like previously said, 10 meters, potentially up to 20 meters depth. And then, some of the other requirements to allow us to be a much smaller footprint, which is a more compact system, which is necessary for the current limitations of actually getting hardware to Mars. And this actually isn't even novel concept for space exploration. So Honeybee developed a system called Lister, which recently was demonstrated on the moon as part of Blue Ghost Mission 1. So very even smaller system actually for doing subsurface thermal analysis on the moon. This happened, I think the operations happened in March or April. And I actually have a video to show you kind of what that looks like from the perspective that we were able to get from one of the cameras on board. So you can see the coiled tubing is already deployed to the surface. It's using its pneumatic gas to penetrate downward as it deploys the coiled tubing. This Lister does not have a rotary percussive drill, so it's limited to a fairly shallow depth. As you get deeper, you get more consolidated regolith, potentially rocks as well. So what we've done on RedWater to kind of de-risk there is we've added rotary percussion at the tip so that if we were to hit some obstacle like that, we could drill through it. A Rodriguez well I previously discussed, so this is not a new concept. It's developed by the U.S. Army in the 60s for remote military camps in the Arctic and Antarctic. It's been highly successful at generating large quantities of water in remote locations for quite some time now. So we've leveraged this concept, and I want to give credit to Dr. Stephen Hoffman, who was kind of the first to present this concept as something for Mars. So a lot of his work was inspiration for what eventually became RedWater. And you can kind of see here on the right our initial proof of concept of creating a Rodwell. And then I won't get into the details here, but just some of the initial modeling efforts to determine, what sort of energy and thermal output is going to be necessary based on the size of the well that's required for any given volume of water requirement. So we initially built this TRL5 brass board version of the system. This allowed us to integrate all the subsystems and validate it as like a single system. We kept some things modular that were still not fully sorted out as far as the exact design. So the injector system, this is something that we had to innovate on because typically in oil and gas, they're using much larger, higher sources of energy to straighten these tubes out. And they even have much larger reels. So we actually have a higher energy requirement when we coil up our tube so tightly. But it's necessary for the volume requirements of current Mars missions. And so we weren't exactly sure how this injector design would shake out. So we kept it sort of modular with additional sets of rollers, the ability to adjust the exact positions. One of the challenges is getting the straightened tube at coming out of here, because you obviously want to go down hole straight. So we use this TRL5 system to sort that out and performed end-to-end testing of this system, including in TVAC. So we successfully did a TVAC test in a Mars-like environment, pumping the chamber down. It was stable somewhere around 5 to 8 torr while we tested, and then we were using active LN2 circulation to actively cool the ice down to minus 70 C. You can kind of see some of the results from that testing. And if I'm going way over, someone stop me. So then so after that round of testing, we were awarded an additional option on funding to advance this to a flight forward design of RedWater. So you can see the repackaging, which somewhat resembles the Lister payload that went to the moon. So just giving us a better overall profile on mass and volume. And then we were able to now constrain our injector to an exact geometry, keep everything more rigid. Used some flight forward components, not entirely. I wouldn't call this exactly TRL6. There's probably a little additional development that would need to go on in sort of the next stage. But it is still, even after these flight forward advancements. It's fairly heavy system. I would say there's still work to be done if we want to not be pushing 100 kilograms on this system. And this particular mass does not include your avionics and your gas. This is just looking at the hardware. That would be the drill itself. So still fairly heavy system. And I should say too, the previous system was scaled back to only be a large enough coil for our T-back chamber, which is about 1.5 meters of depth. And then we actually scaled this one up in the event that there would be future field testing. So this system's capable of around 10 meters of depth. So that's also factored into the mass there. We did so just based on the limitations of this round of testing. We stuck with a freezer test for this version of the system. So we did a full end-to-end test in there in our walk-in freezer, which we can maintain around -10 to -15 C. So not quite Mars temperatures, but enough to keep an ice block frozen. We built a custom ice tower to give us something to drill into. So we purchased these ice sculpture blocks and were able to fuse them together. We did about a 2 meter tall tower. And we use these because they're extremely clear ice, and as we're drilling, we can get good, imaging and video of what's actually going on, and somewhat of a feedback for how the Rodwell is forming versus what our model said. So just a few of the ConOps that we tested here. Initially, you of course need to initially drill to your target depth. So that's what's happening here, pneumatically clearing. You can see the cuttings pneumatically being shot out of the borehole. We did a sort of a hybrid melt drill descent to just see power requirements for that operation, and then an actual like Rodwell formation um, to start generating enough water that we could extract. And then we did our extraction operation and successfully collect a fairly small amount, just based on the limitations of how much you can melt in this size of an ice block. The science application of something like this. So there's the ISRU angle where we need resources. We need water on Mars for propellant manufacturing and life support systems, but there's also objectives to go to Mars and look for life. How do we do that? So there's been past missions to do that, but I think the next step is to penetrate subsurface deeper to look where you have the untouched subsurface that hasn't been touched by radiation and sublimation. So to explore deeper, you're going to need something that goes beyond the top layer there. So we've been working on a technology where at the tip of our drill we could embed instruments like a gamma ray neutron spectrometer, a near infrared fiber for spectroscopy. We could do temperature sensing and heaters for like a conductivity measurement. We even embedded a camera in the tip for context imaging, and all that could go at the tip of something very similar to RedWater, where you have sort of 10 to 20 meter depth range and a similar package. And then you put something like the smart drill that I just showed at the tip of that. This system is very similar to RedWater, except you have your instrumentation suite above that. So not quite. This one is more designed for like a 1 meter class drill where you can put everything right at the tip. In this case, since we have our drilling components in the tip of the drill, we would put science instruments behind that. And then you could also enhance this with cuttings collection at the surface using something like Honeybee's Planet Vac concept of a pneumatic sampling head. And then you could either deploy that with like a robotic arm, or we have another linear deployment stage where you could deploy around your coiled tubing to create a conduit to transfer your cuttings from the surface up to the lander, where you could have additional science operations there with a sample carousel, similar to what we've seen on past missions. But in this case, cuttings are coming from much deeper than just the surface. And that's it. Yeah.
Thank you very much.
Thank you.
We're running a little late. Had the quick Q&A running for very long. Interested in about the size of these things? Can you tell me, right? I think I saw like 600 watts for one of your systems, which seems pretty small. Are you going to scale up to, kilowatts and tens of kilowatts?
Yeah, so the image here is sort of the conceptual one, but yeah, what you saw previously, like as far as drilling and heating operations, which is kind of what we were focused on at this stage, yeah, I would say you expect somewhere between a half to 1 kilowatt, in electrical power coming in. But of course, that continues to scale depending on the secondary operations. Like, well, for starters, you assume you're bringing gas with you, but you could potentially, have a system that's extracting CO2 and compressing it from the atmosphere. That would obviously require additional energy. And then any of the processes that happen after the water collection itself are going to be additional, energy budget there. So
Oh
yeah,
yeah.
those aren't necessarily accounted for in that power figure. That's strictly just the drill and the heating itself for the Rodwell.
Well, thank you very much for that. You had quite it's an honor to be listening to Joey here. The honeybees right at the center of things, actually doing things on Mars. Anyway, we got to wrap it up here. Thank you very much.
You have just heard a talk in the conference for students, The New Future of Making on Mars. People like you are taking part in the exploration of Mars. You can too. This online conference is sponsored by the Mars Society of Canada and MakerWorks of Ann Arbor, Michigan, and organized by Two Planet Steel. Please like, subscribe, and watch more conference videos.